Today we are going to learn about propulsion system.
The learning outcome for this topic are to describe the key element of propulsion system, to explain the basic principle for the different type of propulsion, and to discuss propulsion that produce thrust without mass. To design a specific system, we start with the desired thrust, usually at some very specific time. The propulsion system controller manages this input and formulate command to send to the propellant management actuators to turn the flow of propellant on or off. For some systems, the controller also manages the energy input to the rocket. For example, in an electrodynamic rocket, the system has no interface with the spacecraft electrical power subsystem to ensure it provides the required power. The controller uses sensors extensively to monitor the temperature and pressure of the propellant throughout the system.
There are two classes of rocket which are thermodynamic and electrodynamics. Thermodynamic rocket transfer thermodynamic energy, heat and pressure to a propellant and then convert the energized propellant into high-speed exhaust using nozzle. There are a wide variety of thermodynamic rockets currently available or being considered. We can classify this based on their source of energy. Cold gas propulsion uses mechanical energy of a gas stored under pressure. Chemical propulsion relies on chemical energy from catalytic decomposition or combustion of propellant to produce heat. Solar thermal uses concentrated solar energy to produce heat. Thermoelectric uses the heat produced from electrical resistance. And nuclear thermal uses the heat from a nuclear reaction. Chemical propulsion can be divided into three types: solid, liquid, and hybrid. While liquid is divided into another two types, which are bipropellant and monopropellant. Meanwhile, the electrodynamic rockets that currently in use operationally are ion thruster and plasma thruster. Ion thruster use electric field to accelerate ions, and plasma thruster use electric and magnetic field to accelerate a plasma. This is an example of the cold gas propulsion, where high pressure gas propellant is fed to low pressure nozzle through pressure regulator and then release the gas through nozzle thruster and generate thrust. And normally the propellant that used in this type of propulsion is nitrogen, helium, nitrous oxide and butane.
Chemical propulsion is classified into three types: liquid, solid, and hybrid. In liquid propulsion, the monopropellant chemical rocket uses only a single propellant. These propellants are relatively unstable and easily decomposed through contact with suitable catalysts. The most widely used monopropellant is hydrazine. Bipropellant use two liquid propellants. One is fuel such as liquid hydrogen and one oxidizer such as liquid oxygen. Brought together under pressure in the combustion chamber by the propellant management system, the two compounds chemically react, releasing vast quantities of heat and producing combustion product. Solid rocket contains a mixture of fuel, oxidizer, along with a binder blended in the correct proportion and solidified into a single package called a motor. A typical composite solid rocket fuel is powdered aluminium. The most commonly used solid rocket motor oxidizer is ammonium perchlorate. Hybrid rockets combine aspects of liquid and solid system. A typical hybrid rocket uses a liquid oxidizer and a solid fuel.
The more fuel grain form the combustion chamber and oxidizer is injected into it. A separate sparking system or superheated oxidizer initiates combustion. The most commonly used hybrid propulsion is a sounding rocket.
This is a schematic diagram show the monopropellant system. You can see here the hydrazine and the catalyst nitrogen or helium in one tank.
And this is a schematic diagram of the bipropellant system.
This is a specific impulse comparison in between cold gas, monopropellant hydrazine, solid rocket motors, hybrid rocket, storable bipropellant, and liquid oxygen. Specific impulse depend on many factors such as altitude, nozzle expansion ratio, mixture ratio, and combustion temperature. A solar thermal rocket is a theoretical spacecraft propulsion system that would make use of solar power to directly heat reaction mass and therefore would not require an electrical generator like most other forms of solar-powered propulsion do. The rocket would only have to carry the means of capturing solar energy, such as concentrators and mirrors. The heated propellant would be fed through a conventional rocket nozzle to produce thrust. Its engine thrust would be directly related to the surface area of the solar collector and to the local intensity of the solar radiation. For space application, the energy source is the electrical through a simple resistor or by creating an arc discharge similar to spark plug. We can create heat. Thermoelectric rocket transfer this heat to the propellant by conduction and convection. Example of thermoelectric rocket is resistojet. Another potential useful heat source in space is nuclear energy. On Earth, nuclear reactors harness the heat released by fission of uranium to produce electricity. The nuclear thermal rocket uses its propellant such as liquid hydrogen to flow around nuclear core, absorbing nuclear energy. The propellant enters the reaction chamber where it absorbs the intense heat from the nuclear reaction. From there, thermodynamic expansion through a nozzle produce high thrust and high specific impulse.